All right, good morning and welcome to my second lecture on mass movement, slope stability analysis and stabilization measures. Last week, only a very few of you were here, I think, in that lecture. So I can only recommend you to watch the video online, which is on YouTube. When you reach Schoology, you should be able to see that one. And for those who are not used to that online lecture, I'm Chris Gomez from Kobe University, from the SABO laboratory, Sediment Hazards and Disaster Risk. And this is a lecture for the joint international lecture between the UMS in Indonesia and Kobe University in Japan. And last week we started to talk about landslide and mass movement and debris flow, and this is the continuation lecture. And I will go back on some of the points we saw last week. And as a start, you can see here a coastal landslide. It's a landslide in California, which is called La Conchita landslide, and that's engulfed part of this small town, this small area here in January 2010. And you have the coastal cliff, or the past coastal cliff that went down into the sea. So, no, into the city, sorry, not into the sea. So quite some scary element here. So what did we see last week? So last week I talked to you about Asakura, and we talked about different types of landslides, different types of mass movement. And we explained that depending on the size, the shape, the position of the landslide, and the amount of trees on top, so what is on the slope, you're going to have different type of hazards, different types of impact downstream. And we were talking at that time about the Asakura. We used mostly the Asakura example, if not only the Asakura example, to look at those different landslides and those different trees related, we call it wood, debris, or drifted wood that can enter the system. Now, for this week, we're going to continue on that. I chose to start with the first week, having a concrete example so that you know why you are doing it, why is it important, before starting with the theory. Most of the courses will do the other way around. They will go and give you the theory and show you how you can apply it. I think it's more appealing, if you come to the class, of course, it's more appealing in general to try having the problem in front of us and seeing like, well, that's what we need to understand. This is the problem, and then give you some of the key elements you can work from. So pedagogically, it's very different, but maybe it's also a bit more real in the sense that if you become practitioners, if you become natural hazard specialists, if you work in consultancy company, if you work for your own government in Japan, in Indonesia, or in France, what's going to happen is that you will be confronted to some issues and problems. And most of those problems you will not have learned in the class fully. So you cannot rely only on what you've learned at university. You will need to dig out. You need to learn also new techniques and new methods depending on the problem. And this is the approach I chose here. I decided to show you one set of issues, one problem, and try then to give you some of the elements that you can use, and that will be this lecture today, to solve these issues. I'm using the air conditioning, so it's very dry and maybe drink while I talk. So the objectives of this lecture. In this lecture, you will learn the basic methods to consider slope stability using the factor of safety. We will concentrate on back of the envelope or simple calculations methods that you can use in GIS as well as from data you get from soil mechanic analysis. So I'm not talking about FEM or FDM methods that are used by some computer models. I'm giving you the theory today and how that theory can be used. And the keywords will be the infinite slope model, the Kuhlmann methods, Taylor charts, and the ordinary method of slice. Hold on a second, I'm going to off the air. So those are the major elements we are going to talk about today. Those are the objectives of the lecture. Have you learned those elements and have you integrate those keywords? So when we talk about landslide and mass movement, most landscape contain a different variety of hill slopes that grades down from very steep down to usually a valley or down to the sea. And those slopes, they are not made of bare rock or only of bedrock. They are covered by what we call colluvium and sediments. And that's the main element most of the time, which is going to be at the source of the landslide. You can have also landslides in bedrock, but those are more larger and of a different kind. And usually we divide the different type of mass movement depending on their speed and how wet they are, the kind of material they involve. And here I'm using this is a figure from John Wiley and Sons, where they have solifluction, which is like slow speed, very wet, like movement on the surface mostly. They have what they call the earth flow, which is almost like a debris flow, but it's like more like a rapidly moving landslide. Then they have the mud flow here, which has like really what you imagine almost Banjir type debris flow type, but maybe more rich in fine material. Then you have the debris flow, debris slide. I'm not a very big fan of this debris flow chart here. It doesn't show it very well, I think. Then you have the slump, soil creep, and rockfall. So different conditions, we remember the words more than the images here. Different condition, more wet, more dry, more faster, slower, will define different type of debris flow. And when we look at them one by one, if you look at, for instance, the Oso landslide here, which occurred in 2014, the last time it occurred was in 2014 in Washington. That landslide actually has occurred many, many times. If you read my book on natural hazards and disaster risk, which is coming out this year with Alcantara and other colleagues, we wrote a book which is called Disaster Risk. And in that book, which is published by Routledge, I show the different period of the Oso landslides and the different phase of evolution. It's a very good book. I suggest you go and buy it and read it or borrow it from the library if you prefer. I talked in that book about the Oso landslide, which is here. And when you look at the landslide, you have the typical crown, and you can see the area where the landslide has gone down in this area with the toe and the foot of the landslide right there. And in that case, you see the sloping surface is a bit like this here. It's a bit curved, and that's how it went down. You can see the top part here, which is like what with the crack level. You can still see the top, which is right there, and all the rest of the material that slammed down. But it's not the only type of landslide. You have also landslides that can start with a very linear failure plane, like you have here. So it's not only rotational, it's not only rotational, there are different type of landslide. But let's say for rotational failure, that's one type, but you have other different types. And for those different types, we will use different type of equations, different type of model to know whether they are most likely to occur or not. And this is going to be the main beef for today, try to understand those elements. So if we think about the slope stability concept, to use my pointer, the major way of defining whether or not the slope is going to be stable or is it going to move, and what is its chance of moving, like how much, if we were to put a scale on it, is it most likely to move or not? And to try to define those, we use what we call this factor of safety, or FS. So FS is equal to the maximum shear stress at failure, which is equal to the shear strength, divided by the shear stress that causes the sliding. So you have two different stress. You can think about them as forces as well. It doesn't really depend on how you want to imagine things, but you have two forces that act against one another. One is the one that push things downwards, and one is the things that retain everything. So when you have an FS which is above 1, the slope is somehow safe. When you have an FS which is below 1, then it's going to move. And most engineers, or not most engineers, all engineers will not consider 1 as being safe. They will look at values between 1.3 and 1.5. So that's what I'm writing here. FS, we think that it's usually acceptable when it's between 1.3 and 1.5. Anything above is good, but anything underneath that value of 1.3 to 1.5, that slope, I wouldn't be so sure about it. So if you think about it, you can also look at it as the resisting against the sliding moment. That's what I was telling you. So you can imagine like this resisting moment, like everything doesn't move on the slope. Again, it's everything which is pushing down and pushing it down downstream. Who are you? Sorry, I had some difficulties with my camera. So one of the most popular criterion, way of calculating whether the slope is most likely to move, once we have that concept, is called the Moore-Coulomb failure criterion. Hold on a second. I think there's there is just a chat that was there. I don't know what it was, but it's different. Okay. So sorry for that. So when we think about it, and we think about it as the total stress, okay, we can define the Moore-Coulomb failure criterion as the total normal stress multiplied by the tangent of phi, which is the soil internal friction angle based on the total stress. And C will be the cohesion of the material. So if you are told this and you're like, what does it mean? So C is, let's say when you have mud or when you have like soil and you try to pull it apart, it's going to stick together. It's going to stick on your hand. It's going to be sticky, right? And this is because the material this is the cohesion part. This is in the soil, the cohesion. But the second element here, phi, which is the friction factor, it's the element that keeps the sediment right on the slope. So for instance, I'm going to draw, if I can. Imagine that you have a bucket with some sand inside. di dalam sini ada pasir ya. Pasir, sand, suna 日本語でね。And you drop it down. It's going to create a small mount. Hey, what are you doing? And that's small. This is nothing. Okay, this thing is nothing. That small mount here is going to have an angle, and that's angle here, sorry. That angle is the angle phi. It's not totally true. It needs to be tested under different loads in a machine, but it gives you an idea. That's the slope angle at which the sand will stop moving. So if you have sand which is very irregular, giza giza, that slope can be quite steep, like 38, 39 degrees. But if you have very, very round shaped, then the slope will be much slower, maybe 30, 34 degrees, very, very different. You would tell me 34, 38, not much difference. It is different. When you make the calculation, it makes a very big difference. Now, when you have C5, which is the total normal stress, the vertical stress. So when you're in the slope, the phi is that stress going down, acting on phi, which is a solid internal friction, and having the cohesion. That gives you the total normal stress. And then you can also look at it as the effective normal stress. So to understand effective normal stress, you need to read the book by Terzaghi and Carl von Terzaghi, who's one of the father of civil engineering and rock mechanics and soil mechanics. And he explained in his theory that the role of water and the importance of effective normal stress. I'm not here to explain that to you, but you can also express it as normal stress in this way as well. Okay. Now, when you have this theory in head, it's like, okay, that's the idea. The next things that you need to do, and this is a table by Ming Xiao, I did that in 2015, very good table, so I reuse it. You need to define what type of landslide you're looking at to decide what methods you want to use. First, if we think about the mass method, and this is what we'll do today, we'll look at the mass method of slice. I will talk about it in one slide at the end, so not much. And same for the finite element methods. I'm not even talking about it this time. This is for another more advanced lecture if you're interested. Today, we are going to talk about the mass method. I don't know why it's doing the spike on the left. It's really bothering me. So today we're going to talk about this. And yeah, it's doing it again. So mass method, the sliding soil mass is analyzed as one entity. So we imagine that it's a continuous entity, and that's what we look at. And we think that this whole mass is considered as one homogeneous whole material. And we can use the infinite flow slope methods for dry slope, submerged slopes without seepage or with seepage. I will explain that in a second. And finite slope methods with planar failure, and that's the Kelman's method. We'll go about it in details later. It's a bit difficult to understand the first time, so I advise you to go back to it. You might need to open a book at the same time, but that's for you to do. And the different curved failure surfaces for undrained slope. And we'll talk to you about the Taylor chart I'm not going to talk about the Michalovsky chart this time, only go about the Taylor's chart. And to start, we'll start with the infinite slope model. So that's, I think, the simplest model. That's why we started with it. And we consider soil with a cohesion C, an internal friction angle of 5, and rho will be the unit weight. So we need to define two things. Like what we said earlier, let me go back to that slide. When we are here to calculate Fs, we need the sliding forces or shear stress or moment, depending on how you decide to calculate it, plus everything that stops the sliding. And the infinite slope model does exactly that. It does forces going downwards, forces going upwards. And we have then the shear resistance, which is here T, formulated at W sin beta. So this will be W, that mass here. That mass here is the weight, that moving mass. And beta will be this angle here. You can see the angle of the surface here. And for infinite slope model, we think we reduce the problem to say, well, the infinite slope model is for elements of mass of sediment and soil that will move parallel to the surface. So that angle beta here is the same that this angle here, no change. Beta surface equal the beta underneath the surface where you have the sliding plane. So it's W, the mass, multiplied by the sinus of beta, and that will give you the resistant force, like resisting the movement. And you have the normal force acting vertically, and this is the W and cosinus beta again. It's going to tell you push the material down. When we convert those forces into shear stress and normal stress, then we get those value here, where this is the unit weight. We change from the force to the stress by dividing by the surface. So we get divided by surface, so we get 1 point. So for each of those points, we'll get the unit weight. And it could be H. H is the depth here, multiplied by the cosinus beta by the sinus beta, okay? And same for the normal stress here, YH cos square beta. And this will give you the two stress that will oppose one another to have the Fs value. So you can see here we have like one cos will go down, this cos beta will go as well. So, and we're going to have YH sin beta by Y cos beta being actually the source of the Fs, when we only consider the balance between shear stress and normal stress. So this is very easy because it's only a geometric approach to it, and it reduces to very, very simple elements. So the factor Fs, when we also consider the other elements, which is the cohesion, as we mentioned, reduced to 2CYH sin 2 beta plus tan phi divided by tan beta. And this factor of safety here, you can see there is no water. This is the dry safety factor. This is when you have a dry slope. You're not considering having water inside, just dry slope. Now, if we think about adding water to the mix for a submerged slope with the groundwater table right at the surface and without internal seepage. So we don't let the water go, no seepage. The water doesn't move downstream. It's just there. No force is moving the water. That's for later. The equation then changes as well. And we get this second equation where we have 2c y prime, rho prime h sin 2 beta plus those elements. And the way of thinking here, it's written seepage. So forget about seepage now, no seepage. The water goes down up to the surface. So it's full of water, which is important here, okay? So that equation here was for the dry infinite slope without water, and we had no consideration for the effective stress. We considered the full stress because we had no water. But when we have water inside, we need to consider here the submerged mass. So the sediment is in the water. So before I go further, and you're asking, oh, what is this difference? Well, let's do a bit of a drawing again. Now, imagine that, yeah, why is it doing this? It's really irritating. So imagine you have a slope, and on that slope, you have sediment and water inside. Someone is having his mic or her mic on. Can you shut it down, please? Ya, siapa yang mic ya on ya? Bisa dimatikan ya? Mic dimatikan ya? So you have water in the middle. That water is not going to resist the downward movement when you press normally. So when you have normal stress acting on a mass of sediment, the sediment themselves will resist that movement before sliding. The water does not. So when you think about the total column of mass, out of that mass, there is the mass of the sediment, which is going to contribute to the shear strength, but the water is not going to contribute to the shear strength. And when the sediments are in the water, they are actually like floating in the water still, right? So when you consider their density, the density is the density minus is the density in the water. It's not the density of the sediment dry in the air. It's the density while plunged in the water. Hold on a second. I'm going to try to see who has his mic or her mic on and try to. And here we go. Adania, your mic is on mute. Okay, so let me go back, close that. So you see that's the difference. The difference between the sediment in the water, not so dense, against the sediment dry in the air. They will contribute to the mass in a different way. And that makes a difference between that element here. You see that thing? That prime. This is for the material which is in the water against what we had here. No prime. It means that the water, it's not in the water. So if I go back here, it's the difference between the normal, total normal stress and the effective normal stress. You see, we work with the prime here. We have no prime in that case. This is why I made the difference between total normal stress and effective normal stress. What is in the water and what is not make a difference. And then you get this factor of safety. Okay, so that equation here does not consider water movement, but the water movement is going to create extra stress on the sediment, and that water movement is going to help the material go down and become wasted and become a landslide. So the equation of the saturated unit weight of the material become like this. So this time we are not considering even the material which is dry, we're looking at the saturated material, and to which we have to use the pour water pressure. So that's pressure which is pushing the material and helping it slide down, so that the Fs looks like this. And it can be reduced to that as usual. And that is the equation for saturated material for the infinite slope model when considering seepage, so with seepage. So we have three set of equations. We have first the dry material factor of safety. Two, we have the fully saturated without seepage. And three, we have the infinite slope model with seepage for saturated material. This equation here will be the more complete one when you consider infinite slope model. Now, I'm going to, it's 30 minutes, so I'm going to give you a problem. A natural slope is 50 meters high, and the slope angle is 35 degrees. Underneath the surface, there is a 5 centimeter thick weak layer. So that's going to be your sliding plane. And this layer is located at 80 centimeters depth. So H, 80 centimeter. The surfacial soil layer cohesion is 50 kilonewton per, this should be a square here. Sorry, this is square and cubic. Square meter, and the internal friction angle is 30 degrees with the bulk unit weight of 19 kilonewton per cubic meters. I want you to calculate the factor of safety for the soil layer lying over the weak clay. So you have this weak clay layer. I want you to calculate the factor of safety for the material which is on top. And here you go. You have maybe 10 minutes. And that's when I take a break. Okay, so I'm sure you all have the right answer, and I can give you, you can compare it to what I was expecting. Is it me or? Just a second. That's the technical aspect. And here we go. Having an answer which is already written often stops me from saying something wrong, which is always a good thing when you're doing lecture. Okay, here we are. So I'm still recording. Let me check. All right, so what was the solution of that problem? So like we saw earlier, I was not telling you that we had any water or anything. So it was the simplest answer of all. So you just had to put on the balance using that first equation, just using that bit here, and plug the value in. So I was giving you all the values where C was 15 kilonewton per square meters, phi was 30 degrees, and the density of the material was 19 kilonewton per cubic meters. So since we know that the slope has an angle of 35 degrees, we just had to replace those elements. So 2 times 15 by 19 multiplied by 0.8 sin 2 by 35, and you have a value of 2.92, which is really, really high. So no slope failure. Okay? So very easy, basically. You just have to plug in the number in the equation. So you look at your problem. Do we have water, no water, seepage, no seepage? And choose one of those equations, equation 1, 2, or 3. And then you can get your answer there, okay? So this is very straightforward. I hope that you all got that answer, no slope failure. Now, in that first element, we had the surface and the underneath subsurface, the sliding surface, that are parallel, all the same. What happens if that we slide on a regular linear plane and the top is irregular? What will be the results for that? So there is 100 people to that lecture today. I hope everyone could join in. It looks like I cannot have more than 100 people to that lecture. So my apologies to those of you who try to join in and can't. You will have to wake up earlier next time if you want to be part of it. So I was telling you the previous methods work very well, as long as the two surfaces, like you have ABC here, if ABC and AC, if AB and AC were both parallel, that would be perfect. But when it comes to this kind of wedge type of mass movement, like you will have on the side of the road, or the first image, you know, when I was showing you this, in that case, if the failure plane is linear, we cannot use this. We have to look at another type of model. And for that, we have to use the Kuhlmann method. So in that case, it's the wedge ABC, which is going to fail. We assume that the failure surface is AC. The angle between the horizontal and AC is beta, and the angle theta is along the AC line, which is the sliding plane. And once again, very, 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 very simple method. We consider that the soil density, the cohesion, and the angle of friction, those three elements are the same everywhere. No change within the mass. Everything is the same all around. And for that, we need to use a method that was devised by someone who's named Kuhlmann. Karl Kuhlmann is a German engineer who's right here. And in 1875, he defined a method to work on those planes, those systems. So first, we need to work on the weight of the wedge ABC. And we're going to consider that weight to be W. And one of the way of calculating W is a half of an h square of the cotangent of theta minus the cotangent of beta. And this gives you in 2D, not in 3D, in 2D, the mass of that wedge. And then we follow the same kind of methods. We think about, okay, what are the driving? What is going to bring the material down? What is stopping the material? Then we also define again T and N as our normal stress and the shear stress. And then we have also, we need to calculate AC, which is going to be our sliding plane. So we consider it to be H, which is the height from the point A to B and C. B and C are supposed to be on the same height. We consider even if there is a small variation in topography, you can imagine it's the same altitude. So A and you have B and C on top over there. So H is the sinus of theta theta angle here, so that we can define the shear stress and the normal stress on AC as being T divided by AC1. One is for 1 unit, and N divided by AC1. And the method itself is explained here in this organigram. So we obtain the slope properties. Again, the height of the slope, in order, sorry, the mass density of the material, the height of the slope, the difference between the C at the bottom and the AB at the top. Then the cohesion C, which is right there. The cohesion C, which is right there. And the phi, which is again the material internal angle of friction. And then what we have to do is to assume a value of Fs phi. And then you look at me like, what is Fs phi? So Fs phi is the factor of safety on the basis of phi. So we just consider phi. And we are going to consider here phi m. And phi m is the mobilized internal frictional angle, and it's which is actually developed along the slip surface, also denoted at phi d. And this is how you relate after that the shear stress on M based on phi m and Cm. Okay, and you calculate phi m at tan phi divided by tan phi m, and this gives you what we call Fs phi here. So again, it's very similar. You just need to plug the data in and replace them. And then from that, you can calculate Cm, which is the mobilized cohesion that is actually developed along the slip surface, that is also named Cd, using that equation where Fsc is C on Cm. And then we evaluate whether Fsc is the same as Fs phi. And if it's not the case, then we're going to try again to get closer and closer and closer until Fs equal Fs phi equals Fsc. And then we know that we have our right factor of safety. So it's an iterative method, like in a computer would do, basically, trying to get closer and closer to the right answer. And using those equations, then you can get your Fs, which is equal, in fact, to A, which is right here, a constant A, which is bringing everything together. So it's 7:25 already, so I'm not going to explain in details those equations. Look at them carefully to understand how they bring those different elements together, and how by dividing, only considering phi, only considering C, you can then get your different elements together. So once you have your slope parameters obtained from your favorite machine, this is the whole equation to get your Fs. So if that was a bit like, what do I do? Well, you can use that. You can use this set of equation. You define Fs as Tfs of T like this, and then you can get Fs as C plus phi, I can't remember that, tan phi over the shear stress, which gives you this set of equation here. And it is equal to that set of equation here. So you can see there is a lot of parameters, but it's very simple actually. It's just because you have two different angles. You remember you have that angle beta here and that angle theta here. So you need to actually each time get that one minus that bit here. So that's why equation looks a bit longer, but it's very simple. And at the end, you equal back to that element here. So the easiest way to work is to go to the field, get your data out of your shear stress machine and plugging them back into that equation here. And here there is no unknown. It's all very simple. You have your phi angle, which is right there, which is your, again, internal friction angle. So this you have. If we think about the previous exercise, that was 30 degrees, right? Here you have tan theta. Theta, you have it as well. If we think about the previous exercise, that was 35 degrees. That was the angle of the slope. Theta, we have it here, same. Beta, we didn't have it in the first time, but it's that extra angle we get this time, so you can calculate it. H is the height of your landslide, so this is easy to get as well. This is the density of your material. You have it like in the first time was what, 15 kilonewton per, or 19 kilonewton per cubic meter, sorry. So that's you had as well. And to C, the C was 15 kilonewton per square meter. So we had that as well. So once you have all of this, you can just calculate it very easily, okay? So nothing complicated this time. You should be able to use that equation also in the same way with an example. Now, I've talked to you about plane failure that are linear. So this is for a wedge. And this is for two parallel slopes. So you have the slope and underneath the sliding plane is the same. So we have our beta angle. Oh, that was beta, sorry. The beta angle, which is this angle. And then for the second one, when we have a wedge, we have to get rid of that extra bit of movement to get our angle, and that's what you can use. Now, if we look at curved surfaces, so that was flat, now let's look at curved surfaces. The concept is a bit different. The idea is a bit different. What we look at is a point where we have a rotation, from which we have a rotation. So here, if you have one point, you have you draw a stick or whatever, and you can move on that plane. And that's the round plane that we use, so that we have here the radius, and this is going to be important. So that's what you can see here. You have the O, which is the center of that movement, the center of that circle. This is theta, is the opening between the top of the landslide and the toe at the bottom here. This here, W, is the weight, the mass, which is going to slide. And there is one more extra component. That point here, it's the center, the barycenter of that shape, of that movement. When you take all the mass in that movement, the very, very center of it is W. And if you take and draw a line perpendicular up, the difference between O, the rotation center, and that arm, the L is called the arm of the movement, like an arm like this, is going to be that distance here, okay? So again, unit weight and drain cohesion, friction angle. This time and drain cohesion is going to be Cu, and we calculate the driving moment, md, which is W, this one, multiplied by L. So that's what brings the movement, the element that brings everything down, against what is resisting, what is called here the resisting moment, Mr, which is Cu. It was C before. In the previous set of equations, we just used C, multiplied by R. R is this, it's the radius for R, multiplied by theta. Theta is that angle between that line and that line, multiplied by 1, it's 1 unit, you can forget that. And all of that is multiplied again by R. And that's the resisting moment on this sliding plane, so on this one here. So when we consider the theta angle here, this is what we are interested in. Theta multiplied by R here is a mathematical expression, geometric expression of this sliding plane here. And then what we do is to put Mr over Md, like what we did in the previous equation, so that we get a slope stability factor, factor of safety Fs, right here, to be Cu r squared, multiplied by that theta angle here, divided by W multiplied by L. I'm looking at my screen on my phone, which is what you're seeing, and I see that the whole system is moving super slow because my pointer, the right pointer, is showing something I was showing just a minute ago. So let me change slide and see if it changed slide. And yes, it doesn't. So I will wait for you. I will wait a few seconds for the slide to change. So take a break, take 5-minute breaks for the system to initialize. I think we have a lot of students on the slide. That's the problem. Hari ini karena ada banyak mahasiswa ya, 100 orang, PowerPoint-nya tidak jalan bagus-bagus, itulah terlalu terlambat. Saya akan tunggu 2-3 menit aja ya, karena ya dah jalan memangnya.そう今日本語で言うんだけど、インドネシア語で言ってみたら私のインドネシア語はどうだ最近思ってるけど、喋りながら実は見せてるもの意図が多いからもうすごく遅い。だけどパワーポイントってなんていうの、赤い線のポインターを動かしても私が動かした後あざが見えてるのはもう全然同じ時間にならないから、もうちょっと数秒ぐらいとか数分ぐらいちょっと待ってて、でコンピューターがちょっと元気になるのを待ちます。さっき次の今みんなが見てるスライドを動かしたんですけれども、そのスライドを動かしても全然スマホで見てるから私が見てるスライドと違うので、もう説明はちょっと遅くなるので2、3分待っててください。待っててくださいと言ったところでもう動かしてたらもうそろそろ来てる。Okay, so I think it's fine. Another way of working, then one way of working on this curved surface is to use the Taylor chart for undrained clay with a phi equals 0. And this graphic here is from Mr. Tesaki. So you have the slope of beta, so the slope of the shaman. more I spoke in Japanese and the more my English is gone now. It's terrible. So the slope of the landslide, beta of the surface between 90 degrees and 0 degrees. And here you have unitless elements, NS, which is the density by HC divided by SU mob. This is Japanese as well. The meaning of that is just at the bottom here. Mobilized and drained shear strength, height of the clay slope, unit weight of the clay slope. So that's the element they are using. And you can use this graph to define whether or not your slope is going to be stable or not stable. So, and those different type of graph exist for different type of value. So instead of doing the calculation each time, you can, for a set of value, actually have those different elements. Chart. That chart is also a Taylor chart for C minus phi type of soil. So you have again here the same values and the value of the slope angle here between 90 degrees and 0 degrees. And you can see that for different 5, 25 degrees, 20, 15, 10, and 5, you have those different curves. So depending on the slope angle of your landslide, then you can use actually those charts to define whether they're going to slide or not. And those are all, you have actually table of and pages of those different charts that will help you. Welcome back, Aditya. I can see you.
Hi, Chris. Sorry.
It's okay. You look very busy.
I'm in Jakarta now, actually, with my team. So there is a presentation in JJ. Yeah. Please continue, please.
Good for you. So I'm asking you, saturated and undrained clay slope is 25 meters high. The slope angle is 35 degrees. And subsurface investigation found that the subsoil is homogeneous clays with undrained cohesion of 90 kilonewton per square meter. So that's again here a square that you need. Sorry for that. This is square. And this is square, but this is cubic. And the rock formation was found to be at 50 meters depth below the ground surface. And the question is like, determine the factor of safety. So you should have the PDF with you just in case you don't see all the slides. So remember, we have seen this one, we have seen this graph, and we have seen also this equation here. So try to see how can you plug those different values here. 50 meters depth, 90 kilonewton per square meters of cohesion, CU maybe, and unit weight 19 kilonewton. So what would be the way to actually how could you measure the factor of safety here? So I'm giving you with 39, 10 minutes before it's too late to try to find this one. Very easy. Don't think too hard. Take the equation, put the numbers inside. You should be able to get the answer. Okay, so that was this short interruption for you. So how do you get the answer? So the solution is like earlier. What you need to do is to try to think, okay, what are the equations I can use? And what are the elements that I need for that equation? And in that case, it's one of the first equation that we saw, where we need, which is right here. So we need HC, which is 25 meters, 25 meter high. This is the height of the slope. Beta is the angle of the slope on the surface. We have the weight, which is 19 kilonewton per cubic meters, and Cu, which is 90 kilonewton per square meter. So the depth of the rock layer from the top of the slope is 25 plus 50, which is 75 meters. So based on the previous equation, ND has to be 3.0. And from the figure 5.9 that we saw earlier, you can use ND equal 3.0 and beta 35 to find NS. And when you have NS, then you can calculate SU mob as y sat HC divided by NS, which gives you 85.1 kilonewton per square meter. So you use the graph and use the equations together to get your answer, okay? And once you have that, you can calculate Fs as Cu divided by Su mob, and then you get 1.07. So it's more or less stable, okay? So like the first time, very simple. You use your graph, you read the graph, you get your data from your graph, you plug it into the equation, and then you make the calculation. Now, usually when we use a software, when we make calculation, we know to use two simple methods. We use different types of methods, and one of them is the method of slice. So some of you, especially in Japan, have used HYRCAN as the software, HYRCAN. It's an open source software, very easy to use. And that model is the method of slice. So how does it work? So what it does basically is to slice the slope into different bits. And each slice that you can see here each portion of the slice is going to be able to be calculated this way, okay? And so you have the forces on each single slice, and then you slice 1 plus slice 2 plus slice 3 plus slice 4. It's not a perfect method because it does not consider the forces on each slice. It's one slice alone plus one slice alone. And then there are different ways of working with those slices. You can either, one, add all of them and divide by the number of slices to get an average. Or another method, which gives you the safest approach, will be to take the weakest link. Which one of all of the slices is the weakest slice? And say, well, if one of the slices is weak, that's enough for that whole mass actually to go and start moving. So I think that you should go with the second approach. That's why I mentioned it here in the text. I think it's much safer to consider the approach with the weakest slice rather than taking the addition of all of them. And that's the kind of method that we call method of slice. So in conclusion, we are 10 minutes earlier. When you're assessing the safety of slope, you can use FS, which is a factor of safety, and a factor of safety between 1.3 and 1.5 is a good factor of safety. You can choose your methods based on the type of landslide, the type of slope that you have, and the type of subsurface. For instance, when you are in a volcanic area, when you have volcanoes like at Merapi volcano, you will use the infinite slope model because you have a lot of layers that are parallel to the surface. But when you work with deep landslide and then it's moving on a curved surface, then you can use the Taylor charts to simulate the factor of safety. And when you have a lot of complex slopes with a lot of different elements, that's when actually what we saw today, the infinite slope model or the Taylor charts or the Kuhlmann methods, they are not enough. And then you need to go for other type of more complex system, like the methods of slice. And for the method of slice, there are different type of way of considering them. There is the Bishop method, for instance, and also the Fellenius methods. Those are the two most popular methods. There are plenty of others, but those two are the main, most favorite one and easiest to implement. And even these two methods, they are still very simplified way of thinking about slopes. So most of the time, you will also get, you will need actually to use different type of models. And that's when you start to consider FEM, finite element model, for instance, to see whether the slides are moving. So I'm going to recap today. When you think about the math methods, you have either the infinite slope model or the finite slope methods. And in the infinite slope model methods, you can use submerged slope with drainage or seepage, and dry slope. For finite slope methods, you can have the Kuhlmann method when the failure is straight, or you can use curved surfaces. That's the infinite model. Two parallel slope and under the surface. You can use the Kuhlmann methods when it's a wedge on a regular surface, or you can use the curved surface methods when it's deeper landslide and it's sliding on a rotation, like rotational landslide. And these three methods can be plugged in easily in your favorite QGIS or ArcGIS to measure the slope stability on different locations in Indonesia or anywhere else. Okay, and that's all for today. Do you have any question or anything you would like to ask me before we end? If not, and if it was a bit difficult this time, go back to the equation and try to redo the exercise on your own, looking at the slide and looking at the exercise and how you use actually the different elements. I went quite fast on that part where I didn't talk too much about how to calculate NS and how to get here the different value for CU. So go back to that, look at those graphs and look at the exercise and how you get actually the ND, how you get the NS from those elements and how you can actually read them from the graph. It's very easy, in fact. Once you have it, it's like, oh yeah, easy and quick. So I will see you next week for a last lecture. And for the last lecture, I will talk to you about the tsunami in Banda Aceh in Indonesia. And I will show you something different. We will talk about the importance of combining social science and physical science together to really reduce hazards and disaster risk. Okay, thank you very much. That will be all for today.